Okay, now we're moving on to example number 3 here. And this is one of the questions where I would say it's a lab-based question, or what we call an engaging in argument evidence, a little later on in this question. So one of the things you're going to have to do in your next assessment is to plot a graph, right? So you need to label it. So time is along the x-axis, and theta is along the vertical axis. And then we're going to kind of work out what times you want to have. It looks like I've made nice where I have 0, 1, 2, 3, 4, 5, 6, 7, 8. That's kind of nice actually. And then I got to figure out how many radians. It looks like I can go 1, 2, 3, 4, 5. So then now the next thing after we did the scaling and labeled the axes, we want to plot our points. I'm not going to sit there and do this. I'm just going to do this really quickly. Oh, that was fast. Now what we'll do is put in a line of best fit. Okay, so we're going to try to fit a line through that data as best as we can. Okay, so hopefully we get kind of an equal distribution of number of points above and below the line. And so then that's part A. That's what we call like a C-level question. You should all be able to do that. Moving on to our kind of B-level question is writing the equation for this line. So we need to get two things from this. We need basically the slope of the graph. So when we do a slope, and you're going to do it, say, by hand, you need to pick 2 points on the line of best fit. Now, please don't necessarily pick points that are in your data table. In fact, I would refrain from doing that because sometimes people pick points and the points are not even on the line. So just pick a point, like let's say here, put an X there so I know which point you're picking. Pick another point. You can pick one that kind of like is a nice convenient spot, like 2 seconds. And then you're going to go and do your rise over run. So you have the rise and the run, make your little triangle, and go ahead and calculate that. So your slope, okay, would be your change in theta over change in time, which appears to be, I don't know, it's kind of very rough, but I'm going to say it's looks like 4 rads minus 1 rad all over a time of, I'm going to roughly say that that's like 7.5 seconds. And then this is roughly, well, 2 seconds. So that's about 0.545 rads per second. The next thing is we should probably, didn't really give you a lot of space, is the y-intercept. So I'm just going to eyeball that and kind of assume that it goes down here. And it's close enough to like almost like 0, but it's not quite. So I'm not going to lie. I'm just going to say it's like, I don't know, negative 0.1, let's say. So my y-intercept is negative 0.1 rads. So now we write the equation. So here's our equation. Now our equation, by the way, please do not write y equals mx plus b as you do in math class, because on the y-axis, right, we really don't have y, we have theta. And on the x-axis, we don't really have x, we have time, which is just represented with a t. Okay, so you're going to be writing theta, not y, equals m is our slope, right? It's 0.545 rads per second multiplied by t, and then plus, or I guess actually it's not plus, it's technically minus 0.1 rads. That's our y-intercept. Okay, so there's your equation. Next bit. Suppose that we would like to get the angular displacement when it's at 12.5 seconds. Well, now that you have an equation, of theta versus a function of time. That's 0.545 rads per second times t minus 0.1 rads. So now all you need to do is just plug in at t equals 12.5 seconds into this function. You get 0.545 multiplied by 12.5 minus 0.1. And that gives you a value of around 6.71 rads. Now, if I had made my graph a bit further, I could have extended, which we call extrapolation. We could extrapolate the curve, and then if the graph was made bigger and we could go all the way up to 12.5 seconds, we could just read the value, go all the way up to where it hits the axis, or the line of best fit, and go all across and read the value. But unfortunately, I kind of gave you a point that was outside of our boundary, so I decided just to use mathematics. Next thing, starting at t equals 0, at what time does the wheel reach an angular displacement of 5 radians? So here, yeah, I think, I guess we could just, again, read the value and we could extrapolate if we had made their graph bigger. But I didn't, so I'm going to go with a mathematical approach. So theta equals 0.545t minus 0.1. I'm leaving off the units for now, just to make it a little bit easier to look at. We replace theta with 5, and then we solve for time. So you get like what? 5.1 equals 0.545t. Divide both sides by 0.545, and you get a time of 9.36 seconds. And that's when you reach it. And then hopefully that makes sense. If we were to double check that with our graph, we probably could see like at 9 seconds around here, and then we could kind of extrapolate and see if that works out as well. So if I say graphically, then you should be using the graph. But if I don't say graphically, the more accurate way to do it is actually, or precise way of doing it is using the mathematics and the equation that you developed earlier. Okay, that's it for this example. You can try going on to the next example.